Welcome to Regents Physics Warm-Up. Feel that heat? This is a 7-part review in preparation for the physical setting physics Regents Examination. I, your host, Mr. B, will lead you through not memorization, but process skills. There are many processes involved in completing the Regents Examination successfully. So, let this warm you up, both before you're studying and right before the test. Our video episode today will be Part 4. Sharpshooters in place, pencil. As with all parts of this review, follow these steps both during practice and during the exam. It is not practice that makes perfect, but it is perfect practice that leads to perfect examecution. All right, let's go. So what do we mean up here, pencil? Well, there are significant parts of the examination that require write-up in pencil. Any sort of graphs, any sort of drawings, diagrams. They recommend pencil, and actually it's a great idea because you may change your mind mid-drawing. All right, so let's check out what are all the possible things we may have to do in pencil. First off, simple one, drawing graphs. Now, these are not on every examination. They haven't been in a while. Maybe it's time. So let's check out a few of these. There's some rules here about how you plot your points, line up, etc. Let's go see them in action. Here's a problem. Now, this one involves a data table up top here. And then, along with this data table, we have a grid. So always keep track. Speed, kinetic energy. They don't always put them in XY order. Speed is the x-axis, kinetic energy the y. So make sure you're plotting x, comma, y. Also, don't forget the 0, 0. That is one of the data points, so then it should be on your graph, which you do. You see the little data point down here. If it's not in your table, well, then it's not a point on your graph. Anyway, once you plot your points, you have to be very careful. First off, make sure that your points actually fit where they should be. Double check that, because if you're off by one grid line, you're off into the next box, then you're not going to get credit for this at all. Next, notice the data points. They are not smears like this. That's not okay. You need actually a dot like what you see here on the board. Now finally, you have to decide, is this a line or is this a curve of best fit? Well, if you look at this one, maybe you try to line it up, and it looks like perhaps the ends line up, but it's got a belly. Anytime your graph has a bit of a belly, notice over here, it's kind of got this belly over here, then it's probably a curve of best fit. So how do you make the curve? Basically, connect the dots as smoothly as you can. So we like to call this get your art hand on. Do a couple of practice swings with your hand. Then when you feel like you more or less are on target, take a stab at it. Here we go. Notice, graph's a little lumpy. It's not great. However, this is good enough to get you credit. So do your best to try to smooth it out. You want to erase it and go again, go ahead. Just make sure your data points don't disappear. Now, you may also be asked to plot a graph similar to this one. Now, yeah, they have some extra things, like notice question 61 asked you to actually set the axis. So noticing that in the force table you have to get up to 2.5, just set some reasonable increment that you actually make it. Beware, this one is very nice to you. They actually go by 0.5 newtons. Sometimes they don't, because they go by irregular amounts in the table. You still need regular spacing over here on your axis. You cannot go 0.7, then 1, then 1.2. You have to adjust it so that it's even all the way through. Okay, starting at 0, of course. This one, notice, does not appear to have a belly anywhere. This one actually would be best suited by a line. So, let's do that. You take your straight edge, you can bring it over here. Now, this is called a line of best fit, not a line of perfect fit, because the line will not, usually not, go through every data point. If you notice here, I'll do this little back and forth, kind of just trying to straddle these points so that I get a nice line. Now, that's not too bad. If you notice my lower left and then A couple here are on one side of the ruler, and then there are a couple that are blocked that are on the other side of the ruler. Maybe I'd even move it over slightly more, something like this. And then you have to actually draw your line. So, just a nice thin blue line. And when you do it, be sure to go through the edges of the grid. So maybe this is good. Now, of course, if I had a ruler and a pencil, it'd be a little easier than working on this board. I can move my line back and forth, but actually this is not so bad. Notice we have a data point on the upper side, but then we have one on the lower side to kind of balance it out. Yeah, not too bad. Okay. One of the things they may ask you to do, of course, is question 64. So up here, if you did a curve of best fit, they're not going to ask you to determine the slope. There is no the slope for a curve. A curve has a changing slope. However, if you get a line, you are often asked to determine the slope, such as question 64. Beware, the grader is actually going to look to see that your slope matches your line, not your neighbor's line, not some other line, your line. So whatever your line is, you have to do the slope. We'll talk about doing the slope in a minute, but quick answer here in terms of how to deal with the slope. Well, they didn't actually say the word slope in question 64. They say calculate the spring constant. And so one of your jobs is to say, well, how do I get spring constant from a force versus elongation graph? One of the first things to do, of course, is say force is X and elongation is X. So how do those two combine to give us spring constant? Oh, mechanics, here it is. You'll actually find an equation that combines force and elongation. Here it is. The force in this case, of course, is the force on a spring. How can you make it so that these two get you your spring constant? We'll rearrange that equation. Fs equals Kx. The quick rearrange, spring constant would be Fs over X. This is telling you Fs over X. Fs is your y-axis. X is your x-axis. This is really rise over run, or delta y over delta x. This is telling you do slope. When you have a graph, use a graph technique. When you have a graph, use a graph technique. So slope would be the method, and you would actually go and figure out slope, which we'll talk about in just a minute. Okay. Now, how do I determine the slope of a graph? I'm actually going to add a little comment to this. How do I determine the slope and area of a graph? Because those two have been fairly popular on Regents of late. So the method for dealing with slope or for dealing with area is essentially you must actually do slope or you must actually do area. So for doing slope, we have the method described right here. We'll also go live through it. For doing area, we could put it over here in the margin. Essentially, you actually have to do area. And we'll practice that in just a minute as well. But doing area will mean, typically, your area is going to be a triangle, which would be 1/2 base times height, or your area will be a rectangle, which is just base times height, or your area will be a combination of the two, in which case you add them and you'll get your total area. Often that's a trapezoid. Not as commonly asked. There is a trapezoid area formula. If you know it, great. If you don't worry. You don't need to. Okay, let's go over here. Let's check out doing slope and area. Here's a nice problem. The graph below represents force and distance. Now, again, if you see a graph, use a graph technique. See a graph, use graph technique. Now, the most common graph technique, of course, is just looking. Like, the distance is 3, what's the force required? This graph's a little difficult for that one, but let me easier one. Distance of 1.5, what's the force? That's called a direct read. But more commonly, the graph techniques you have to think about will be determining the slope or determining the area. So you keep those two in mind. They often come into play. This question says how much total work is done. Well, first thing I say is, all right, I want work. Good. Do I see work? No. So I need to dig deeper. Let's look at these other graph techniques, slope and area. And I'll ask myself, does the slope of this graph give me work? Well, the slope is rise over run, which is the force over the distance, really delta force over delta distance. But does that equal work? Oh, PRT. This is where you have to be sharp. Does F over D equal W? F times D equals W. So no, slope is not the method to determine this problem. So let's try a different method. We tried slope, let's try area. Does the area equal work? Well, let's see. Area is base times height. That's actually force times distance. Does that equal work? Well, of course, we see it right there. It does. Now, here's the spot where people get caught. They say, oh, F times D. And they jump over here to the end of the graph, and they see the force is 20,000 newtons. The distance is 9 meters. 20,000 times 9, 180,000. Here's my answer choice, done. And, of course, you would be wrong, because you still have to go back and do area. Area is a base times a height. Looking at the base and the height, you see, this area does represent work, but you still must do area. And the only way you're going to do it here is you have two separate rectangles. So the area of, let's call it rectangle 1 and rectangle 2. Here's rectangle 1. To find that area actually is a pretty easy thing. And here's rectangle 2. To find that area is a pretty easy thing. You're just doing base times height. So for rectangle 1, your base is 3. Your height is 10,000. So 3 times 10,000, that gives you your 30,000. 3 times 10 to the 4th joules. And then for rectangle B, or rectangle 2, excuse me, this is a 6-meter base and a 20,000 meter height, 20,000 Newton height, excuse me. So 6 meters times 20,000, that gives you your 120,000, or 12 times 10 to the 4th joule. And of course, you have to add these two together, and that gives you your 150,000, not 180,000. Correct answer. Here's another example down here. The Regents has been very fond of this sort of phrasing lately as well. Not actually having you calculate the slope, but just saying what quantity is represented by the slope of the graph. Well, actually do slope. Easiest way is to say slope is rise over run, and then you just look at your picture. The rise is speed, write it in symbols. The run is time, write it in symbols. Really, it's rise and run are a delta concept. So really, this is delta V over delta T. And of course, what does that represent? PRT. Look it up. Delta V over delta T. Boom. There it is. Acceleration is what the slope represents. They even ask you 63, 64, which some people don't realize, calculate the distance the marble travels during the first 3 seconds. Well, how can you get distance from a speed versus time graph? Now, admittedly, you can do this one with just regular old kinematics. You now know the acceleration from up here. You also know first 3 seconds, that at 0 and then at 3, you know the VI is 0. You know the VF, run over here, is 4 meters per second. You know the time is 3 seconds. And so you have to find the distance. Well, that's a pretty easy kinematics problem. But there's another way to skin this cat, and it's not bad practice. That is, how can you get distance from a speed versus time graph? Well, we should know it's not slope because we just saw slope gives you acceleration. The other option is area. Does area actually give you the distance of a speed time? Well, here's how we check. Speed times time, or time times speed, either way you want to look at it. Base times height. Does that equal distance? Well, come back over here and give it a look. if you rearrange this equation, cross multiply, VT does equal D. So yes, and then you must do area. The way, of course, you would do area is you would go up to the point they said, 3 seconds, and just calculate this area, the area of a triangle, and it does come out correct. All right. Here's another one. Now, we're not actually going to go through the details of this one, but very similar to what's above, and again, it's worth mentioning because it's very common. When they say determine the acceleration due to gravity, symbols, graph technique. Symbols, graph technique. So weight, look it up, FG. Mass, look it up, M. Acceleration due to gravity, sure, it can be A, but it also goes by the letter G. And so when they say determine G, well, you look. Remember, use a graph technique when you're working on a graph. G is not up here, so we need some other method. Let's try slope. Will slope do it? Well, slope would be rise over run, or FG over M. Does that equal G? PRT. Oh, look at that. This one's actually all set for us. FG over M, there's G, good. And then one last example. And again, this has been somewhat popular on recent Regents. The shaded area represents. No numbers on here. You're not calculating anything. But shaded area is pretty straightforward. You just have to do area. Well, area is base times height. So here, the base is time. The height is velocity. And if you're not sure what that is, OPRT. Are there any of these that look like this? Well, none of them say TV right away. But we can find one that has T and V and see, oh, wait a minute. See, this one does. However, you want to multiply T and V, not divide them. So, cross and put this over 1, do a little hot dog, butterfly wings, whatever you want to call it. Cross multiply, you get V times T equals D. So D is your answer. Done. Okay, here's approaching your graphs. Let's come on down over here. How do I sketch a circuit?
Good morning. If questions to me or Ms. Crowley are in, can you please call my office 4405? Thank you.
All right, pardon that. How do I sketch a circuit? So sketching a circuit's a pretty easy thing. However, you just have to set it up cleanly. Again, use pencil. Okay, a student constructed a series circuit. Well, series, you should know, is in a row. So this one's actually easier to draw in some regard. It's got a battery, it's got a lamp, and it's got a resistor. No meters. So be careful with that. Sometimes there are meters, and they ask you to draw them, and you have to draw them correctly. If you don't, you're not going to get it. They won't give you the credit. All right. Even though here they told you the total current, they did not tell you to draw an ammeter in there. So we have to draw this. Well, fortunately, we have symbols. And those symbols are what they expect you to use. So make this series circuit. The easiest thing to start with is the battery. Now notice the battery. Look at all the glory that is the battery. Whether you orient this right, the way it's there, or upside down, or rotated, really doesn't matter. What does matter, little, big, put 2 hands on the end to hold. That's it. Please, do not have some sketch like this. It's really difficult to tell for the grader, what am I looking at? Do I give credit? This is nonsense. Make it look like the battery. Now, it's a series circuit, so just make things in a row. It's also got a lamp and a resistor. Well, here's a lamp, like the old Hostess cupcake. So just put it over here, let's say. Lamp. There's little frosting swirls. Notice all these things have 2 hands. Those 2 hands are where you connect. So we got our lamp. We got our battery. We need a resistor. And the resistor, you can put it wherever you want. You could squeeze it here. You could put it over here. I'll put it down here. I like to make a nice squared off series circuit. A few zigzags. Don't worry, no one's counting. And actually, I recommend you add hands to that. Nice horizontal hands. You don't see them over here, but that makes it easier because now it's very clean where you connect. Connect, connect, connect. No, this does not have to be square, but it tends to give you a nicer picture. There we go. That's a series circuit. Done. Gets you the credit. There's another one. The Regents is somewhat partial to parallel circuits. So series does show up, but the bigger problems, the 4 or 5 point questions at the end, the sketches typically are parallel circuits. So let's check this one out. Here's a resistor and a resistor are connected in parallel with a battery. A single ammeter. Watch out. Now, it's connected to measure the total current of the circuit, so that does matter. When you draw a parallel circuit, PRT, here's how I recommend you set it up. So we have our battery. Let's put that in. This time I'll flip it. Last time we started little. Let's go big, little, put the hands on. Parallel circuit, if you imagine this battery is kind of oriented in like a vertical way, well, move over to the right and orient your first resistor the same way. So I'm going to make my resistor vertical, put hands on it, and then move over to the right again and orient the next resistor in a parallel way. This is a nice setup. Let's move this out of the way. A nice setup for sketching your parallel circuit. Now, one of the things you have to worry about is that there's an ammeter, and the ammeter cannot just go wherever. You can imagine in a parallel circuit what we're going to end up doing. You're going to have a connection to the battery here, and then there's a secondary branch. There's your parallel circuit. Now, in this setup, there are actually 3 different locations for an ammeter. One location would be out in this branch. Anywhere out in this branch covers this resistor. That's the current through that branch. There's a second location it can go, which is anywhere between here and here. So anywhere in this, what seems like a smaller branch, but really it's just a diagram, it's the same thing, would be a different current. Finally, you have anywhere from here to here all the way around this side by the battery. Anywhere in that loop that includes the battery only, that's actually going to give you the total current in the circuit. So when this question says they want a single ammeter to measure the total current, that's the one they're looking for. So the single ammeter to measure the total current, whether you put it down here or up here, doesn't matter. I'll put one right here. An ammeter, secret identity, the hippie wants to hold hands, so you put it in series, put it in the circuit, and then connect all your wires. Hey, man. There you go. There it is. Full credit, nice parallel circuit with an ammeter that measures the total current in the circuit. Actually, let's add this in here. Just to show you how to put a voltmeter in. A voltmeter connects in parallel. A voltmeter, secret identity, the vulture. So it swoops in. Heats up that resistor. A voltmeter always connects on the outside or around the circuit, something like that. So we don't need a voltmeter in this problem, so we're going to take them away. But just beware, the voltmeter connects in parallel along the outside of the circuit versus the ammeter, which connects in series, connects within the circuit. Okay. How do I sketch projectile trajectory? Used to be more common than what it is. Just beware, the moment a projectile is either, well, the moment an object becomes a projectile, let's be very clear about this. A projectile is under the influence of gravity only. Influence of Fg only, the force of gravity only. So while it's in your hand or while it's on your foot as you kick it, it's not a projectile yet. Only once you've let it go, now it's a projectile. When it hits the ground, it's no longer a projectile. So just beware, the problems of projectiles are only while it's under the influence of gravity. Now, that being said, if you notice this picture here on the left, this is like Wile E. Coyote runs off the cliff, and then at some point over here looks down and realizes he needs to fall. That doesn't actually happen, of course. This arrow represents the velocity vector. It's just saying the velocity is to the left of a certain magnitude. What actually happens to the path is what you see here on the right. It begins falling immediately. Same thing's the case here with this angled projectile. It does not follow the arrow and then start curving. It actually starts curving immediately. Okay, if you get asked to draw a projectile trajectory, well, you should feel lucky. Just make a nice parabola. All right, let's go over here. How do I draw the resultant vector? Okay, this actually is pretty common. In fact, often you'll see it as a 3, 4, or 5-point question. So let's check this out. There's some methods here we've talked about. Circle the start, X the finish. Essentially, you want to set this up the way we're going to practice, and you really want a neat arrowhead. Do not add on those sloppy arrowheads. Let's go over here. All right, so a hiker starts at point P and walks. One of the simplest things you can do when looking at components and resultants, okay, is the following. Here's one component from P to the end, and here's a second from this point up north at 1.4 kilometers. Very simple thing is just look. Which way are these two pointing? Well, the first component is pointing to the right. The second component is pointing up. So, if one component is right and the other component is up, when you combine the two to make a resultant, the resultant, of course, should be both right and up, or people prefer to say up and to the right. So your answer should not be anything like this. That's up and to the left. That can't be the answer. It has to be up and to the right. Okay. Now, there are other pieces that come into these diagrams. You got to be sharp on all of them. This is sort of one that people underestimate. Oh, this is easy. I don't have to worry about it. Well, worry about it. Let's check it out. They often tell you to determine the scale used in the diagram. Take your ruler. Use the pinky rule if you don't remember which is what in terms of millimeters and centimeters. And you'll find that this 2 kilometer vector from the middle of point P to the tip of that arrow looks like it's about 5 centimeters. So you can write for yourself 2 kilometers is 5 centimeters. Now, if they left it open-ended for you, then this will typically have something set up like the following. Blank kilometers equals blank centimeters, although they're not always that free. Sometimes you actually have some restrictions on this. For example, they'll say 1 centimeter. Now, you don't have a choice, but this is a pretty easy thing to figure out, because if you want to turn this into 1 centimeter, well, right now it's 5 centimeters. Of course, you can do a proportion. 5 centimeters is to 1 centimeter as 2 kilometers is to blank. Or you could just, all right, I've got a 5. Let me divide both sides by this 5. And so this will now leave us with 1 centimeter. And the other side, 2 divide 5 is going to give you 0.4 kilometers. So your answer in the booklet would be something like this. So be careful with that. You have to actually pay attention and go through the points. Though it seems easy, it can certainly catch you. Next question is often asked is construct the resultant. Now, the word displacement is a common one that shows up here. Displacement is, by definition, a resultant. Often the resultants will be a displacement, a resultant velocity, occasionally a resultant acceleration, but I wouldn't bet on that, or a resultant force, also known as your net force. The most common would most likely be your net force and your displacement. 2 resultant concepts that we use a lot. All right, so we need to actually sketch this and do this. So in this case, since we know we're going right and up, then this idea of completing the triangle up and to the right, well, that may be reasonable. Now, the method we talked about in class was circle the start, X the finish. A bare tail. This is a bare tail. That's where you start your problem. So I'll circle here. If I follow that arrow to the right, it connects me to the next arrow, which leads me up. I have one start, one finish. That looks good. Do not sketch this resultant. Please get a ruler, get a straight edge. You have to construct this thing beautifully. If it's any bit off, you don't have much wiggle room on this. 2 millimeters. And you're not going to get credit. All right, so a little hard for me to manipulate this on the board, but we need an arrow. Let's make this red. I'm going to go directly from the start exactly to the finish. Let's see here. A little bit on the long side, something like that. Now, when you do this, you're going to have to draw this in yourself, of course. You don't have an arrowhead that comes with yours. So here's what you're going to set up. You're going to draw your body of the arrow very neatly. You draw the body of the arrow something like this. And how is it then that you're going to put a head on this? The worst thing you can do is come over here and measure this out nice and neat. It's just the right length, and then you do this. Just killed it. No credit. What you did there is you extended the length of your vector. So while it was supposed to be, whatever it is here, your arrowhead literally added 1, 2, 3, 4 millimeters. You only get 2 millimeters to miss. So you just got no credit. Do not do that. Instead, let's bring this over here. Let's be very clear. This over here is not good. No good. What is good is you go to the tip of your line and drag backwards. One side at a time. Drag back, drag back. There it is. And so I have not actually extended the length of my vector. Key. All right. Determine the magnitude of the resultant displacement. There are actually a couple of ways to do this. You actually can do this just by measuring your resultant displacement and then using the scale that you determined up here to convert it back to kilometers. Do not leave it in centimeters. When the question asks the magnitude of the displacement, they're not asking for how many centimeters on the piece of paper. They're asking for what it actually represents, in this case in kilometers. Of course, you have the other option of Pythagorean's theorem. It's up to you how you want to do it. Finally, using a protractor, determine the angle between the hiker's resultant displacement, the angle between east and the hiker's resultant. Now, this one has been used as a tricky problem. In this case, it's actually not a tricky problem because the angle you would expect. But watch out for this one. They say between east and resultant. So go and identify them. This one is east. Let's see here. This is east. This is resultant. So it's this angle they're concerned with. You may be saying, oh, so what? That's always the angle we're concerned with. Well, let me get back to that in just a moment. Line up your protractor because the question did say using a protractor, which means the answer has to match your picture. Now, no matter how good you are with these protractors, please count the degrees. Here we go. That's 10, 20, 30. Looks like somewhere around 34, 35. Could be 34.5 degrees for my diagram. Yours may be a little different. The reason I warn you on this one, in addition to measuring it, is recently they've been asking this question more along the lines of determine the angle between north and the hiker's resultant displacement, which is not the angle you would expect. But if you just look up here, it's actually not a difficult problem. This vertical vector over here is north, and so the angle between north and the resultant would just be this angle. It's not a hard angle to measure. You just have to realize it's what they're asking. Okay. Similar problem down here. We do not need to go through all the details of it. Here's the same. Determine the scale. This one asks you to draw the resultant, and this is the one actually I like a bit because this is the one that forces you to consider the directions of the components. Notice, one component points up, the other component points to the right, or you can alternately phrase this as one component points north, the other points east. So what will be the resultant of north and east? Obviously, hopefully, it is northeast. So when you come over here and you feel the urge to just connect, no, do not connect those two. That does not point northeast. In fact, people often do that and then don't know where to put the arrowhead because it's not southeast and it's not northwest. So let me just draw a triangle and keep it moving. Do not do that. This is north and east. So the resultant must be somewhere in this vicinity to the northeast. Now, how much north and how much east, this is actually not magic at all. It should be exactly this amount north and exactly this amount east. Well, how do you make it exactly that amount? Essentially, if you want to do this graphically, make this into a rectangle. So you can take your protractor, bring it up to the spot where north ends. Make sure you are lined up neatly. Notice this line on the protractor lines up with the vector. Then mark the 90-degree position. There it is. You could take your protractor, turn it over, line these two up, and just put a dashed line off into that direction. Something like this. Doesn't matter if it goes past the point. Let it go past the point. Do the same thing with the bottom. We want to make a nice, clean, squared off rectangle. So somewhere around that spot. The nice thing you'll have, although I do have erasable ink, you will be able to move your protractor around a little more easily than I can. So I'll mark the 90-degree spot, turn this, line up the straight edge, and run this one all the way up, and check it out. Look at where they cross. That is northeast. You can actually come over there and nestle your little arrowhead right into that spot. That's where my resultant's going to be. Make sure we can see the arrowhead. And then, of course, most of you are using a protractor straight edge. Line that up over here again. We do have full 1-foot rulers just in case you don't have enough length in the protractor. And then connect. Good. You get your resultant vector. North and east, or up and right, as we would expect, as it should be. Good. Finally, look at question 54. That's what I was warning you about. Look at that question 54. Find the angle between north and the resultant. Well, you can do this actually two different ways. It gives you the same answer. This is north, so you can use this vector and the resultant, so it's this angle. Or we also, in a sense, we translated our north over to this side, so it actually would be this angle as well. It's the same angle. It doesn't matter which way you do it. Just beware. It's between north and the resultant. Read that carefully. Otherwise, you know how to use a protractor, but you don't know how to watch for the slips, tricks, and tomfoolery. Okay, now, you may say, oh, 1 page done finally. Oh, no. Oh, there's a lot of dip on these pages, a lot of husk on these two. That's all right. We're almost there. This is really, they're too heavy. This is probably the heaviest part of our video series, so keep going. You're halfway there. Keep going. All right. How do I sketch light ray diagrams? Well, there are a couple of views you tend to get with light diagrams. One of them is the aerial view. The aerial view usually looks something like what you see here on the right, where you have this equal spacing of these parallel lines. Now, those are called wavefronts. In general, this spacing here, this is the source. Maybe this is a stick and a piece of water. Maybe this is a speaker. Whatever it is, generally that spacing is not the spacing to measure. Come over here between any of the other wavefronts and you should get a consistent wavelength, unless, of course, you're playing with the Doppler effect. These drawings, typically, though, they're not going to mess with Doppler. So you may have to measure that spacing. Let's go check out a couple problems like that. And also here, well, we'll look at this. The wavefront's the one that usually requires a little more explanation. Here we go. Here's wavefronts. So what you should pick up right away is that this spacing, that's a wavelength. That's a wavelength. That's a wavelength. That wavelength is not changing. In fact, once a wave is created, so there's some source over here that's then made these waves. These waves have already been created. They're on their way out into the world. Once they're created, in general, as long as you stay in the same medium, everything stays the same about the wave other than the amplitude. So if it's sound, it gets quieter. If it's light, it gets dimmer. But otherwise, the speed, the frequency, the wavelength, the period, those things all stay the same. Okay, so here they tell you the size of the opening is 1/2 the wavelength. You don't have to worry about that other than to know for diffraction, basically to maximize diffraction, you always want the wavelength to be bigger than the opening. So a big wavelength, small opening. Anyway, that's a separate topic. So it says draw at least 3 wavefronts. Well, probably the easiest thing for you to do is measure these. Now you can approximately measure them, but you should be pretty close. So this spacing from here to here, I'm going to try to repeat that spacing to like maybe here, and then repeat that spacing again to maybe like here, and here, here, here. Now you can do this with a ruler, but you want to keep that spacing pretty consistent. Now this said draw at least 3 wavefronts after they've passed through. What that means is you're not getting credit for this one. However, that may help you keep track of what's going on. At this point from diffraction, you know they curve, so let's curve this one back. But the key idea they're looking for, in addition to the curve, is that the wavelength stays the same. So this one, be careful. A common mistake is to do the following. Is you kind of cinch it here. You get a little too close to each other. That wavelength is not maintained. Don't do that. What you want to do is try to maintain the wavelength all the way back to the wall. Keep the spacing the same all the way back to the wall. Now my picture is certainly not perfect, but if you can do something like this, you get yourself full credit. If you want to even be more careful, measure this spacing with a ruler and make sure that this spacing, this spacing, this spacing are all the same. Okay. Now the type that's a bit more common, of course, is your ray diagram. So this is a wavefront diagram. Here's your ray diagram. Now there are a number of things about the ray diagram you have to be careful about. Number one, you better know which angles they're talking about. So they'll give you a diagram. Now this is your classic diagram. Nice horizontal boundary. This is your boundary. The normal line is always, of course, perpendicular to the boundary. We generally draw it dashed because it's make-believe. Nothing bounces off of it. It's just the way we keep track of our angles. And so you go to the normal line, and then you move away from it until you hit your light ray. There's your angle. That's called our angle of incidence. That's our 35 degrees. Now, as I'll show you below, the test likes to check that you know what the angle of incidence is actually referring to. And we'll see what we mean by that in a moment. Now, one of the questions here, what's the angle of reflection? Well, you should know law of reflection. This isn't really about that, this review. This is more about just the process. But hopefully you know if the incident angle here is 35, you know the reflected ray is also 35. Reflection, of course, stays in the same medium. So if we have our quadrants 1, 2, 3, 4, I don't like math class, the incident ray in this case, look at the arrowhead, the incident ray came in quadrant 3. So the reflected ray, boom, boom, will bounce off into quadrant 4. The angle, of course, should be 35. There are different ways to do this. One way is to bring your protractor over here, line it up just right along the normal, where the crosshair hits, and along the boundary. And then say, okay, I need to be 35 degrees. Well, 35 degrees where? Away from the normal. This is the normal. So 10, 20, 35. I put a little dot here. That's the direction I'm going to go. No matter how you hold your protractor, this process is the same. So I can move this way. Makes no difference. I'm going to count 10, 20, 35. It's a little off here because our protractor is not great in this program, but if you do this with your actual physical protractor, this should be the same regardless. And you set up the protractor as a straight edge, or if you have a ruler, you can use that. And that dot, the only thing that dot tells you is which way to go. It does not tell you how far to go. You can go beyond the dot, you can stop short of the dot. But beware here, you are actually drawing this with a physical pencil. A pencil point has thickness. Depending on how sharp your pencil point is, it has varying degrees of thickness. So make sure that when you set this up, you leave yourself a little bit of room here and here so that your pencil actually, the mark actually ends at that point and at that or along that point. So in this case, we'll do something like this. I would go past the dot. Something like this. Just, if you notice, mine seems to line up at that intersection point and go through the dot. That's what you want. If you miss, erase it and do it again. Okay, so the angle of reflection then is, of course, 35 degrees. Now, it says calculate the angle of refraction. You do that with Snell's law. N1 sine theta 1 equals N2 sine theta 2. In this case, it comes out somewhere between, depending on how you did it, 49 to 50 degrees. I actually think it rounds closer to 50 degrees. All right. Now, they didn't ask you to draw the refracted ray, but we'll talk about drawing the refracted ray anyway because that's actually the more common ask. So where would the refracted ray go? Refracted, of course, is moving from one medium to another, so your ray would have to go from water into air. So quadrant 4 is out. Where would it go in the air? Well, generally speaking, it follows the rough direction it was going. So it's going up and to the right. It's going to continue up and to the right. It's going to go into quadrant 1. Now, if that angle is 50 degrees, how do you do that? Well, it's 50 degrees away from the normal line. So set your protractor. Whether you set it this way or whether you set it the other way, it makes no difference. Just count 10, 20, 30, 40, 50. Here it is. If you set your protractor this way, you'll get roughly the same thing. Notice our mark lines up over here. I know it says 40, but that doesn't matter. 10, 20, 30, 40, 50. It's at the same spot. Don't trust the numbers on the protractor. Trust your ability to count. So your refracted ray would then go right around here. Of course, leave thickness for your pencil, which I'm cheating on a little bit here because of the computer. And boom, there's your refracted ray. Now, there is no dedicated symbol for angle of refraction in your reference table. So maybe you want to write theta refract. And that one is your 50 degrees, your 49 to 50 degrees. There it is. Looks nice. Okay. Now, warning. Here are two diagrams from recent exams where your ability to know the incident and refracted angle is tested. Notice here on the left, your entire diagram has been rotated from what you are accustomed to. Unknown material air, this is the boundary. This is the normal line. This, away from the normal, is your angle of incidence. And this, away from the normal, is your angle of refraction. So beware. They're checking to see if you're actually checking to see. Here's another one that was offered recently, I believe 2016. Bunch of angles, which matter? Go to the normal. Here's the normal. Away from the normal, there's your angle of incidence. Away from the normal, there's your angle of refraction. The 63 and 49 are mathematically correct, but they don't have anything to do with numbers you're going to punch into an equation. Okay, good. Almost there. How do I graph a proper wave on scaled axes? We've practiced this quite a bit, and there are some steps over here. We'll just go over them. We'll live them. There are a couple files which all of you have access to called sketching, wave, etc. in the big drawings folder. And so that actually shows you step by step a number of waves how to do this. So the other way of sketching proper waves, we sometimes have to make simpler superposition graphs. So let's go check all this out. Here's a nice one. On the centimeter grid, usually they actually give you a numbered axis, but in this case they said centimeter grid. That means from here to here is 1 centimeter. It means from here to here is 1 centimeter. If you put a ruler on it in your test booklet, it would be that anyway. All right, draw at least one cycle. Now beware here. It says always says at least one cycle. If it's at least one, you can draw one. If you're going to draw two, you need to be disciplined about it. So a periodic, this is a key word. All your waves will be periodic, but periodic means symmetric. And symmetry is your friend. Transverse, of course, is the one they'll typically have you draw. It looks like a snake, a sine curve. And so how do we do this? Step one, amplitude. Amplitude of 2 centimeters. That means the wave goes both up and down away from equilibrium by 2 centimeters. So here's your 0 line. Here's 1. Here's 2 centimeters. Here's -1. Here's -2 centimeters. Literally do this. Take your pencil, go to the 2 centimeter line, and run a line straight across your grid. Do the same thing at -2. Please don't try to be smarter than the problem. Just do it. Now, we know where our wave will live. It has to live between those two lines, just touching them. Not coming short, not overextending, just touching those lines. Now, we have a wavelength of 6 centimeters. Here's where our 3-word definition comes in handy. Wavelength, 3-word definition was distance per cycle. So if the wavelength is 6 centimeters, well, that just means 6 centimeters per cycle, or per wave. So, mark your start and end points. The wave starts at 0 and it ends at 1, 2, 3, 4, 5, 6 centimeters. Good. Now this is where our whole symmetry comes in. Just think symmetry. Periodic means symmetric. Periodic means symmetric. Everything we do in here, periodic. Okay. Now, the wave starts at 0, ends at 6. Where will be the midpoint of the wave? Boom, at 3. That's where it'll cross the axis. Put a little X there. Then, where will it hit a crest and a trough? Well, boom, midpoints again. From 0 to 3, in between is 1.5. That's where it'll hit a crest. From 3 to 6, in between, that's where it'll hit a trough at 4.5. Now, I'll tell you straight away, you do not have to begin with a crest and then go to a trough. You could do trough first, crest second. Heck, you don't even have to start at equilibrium. You could start at a crest and end at a crest. But this is probably the easiest and simplest way. What do you do now? Connect the dots. Do not miss the dots. Do not miss the dots. You may say, I can't draw. It doesn't matter. As long as you hit the dots, you will get your credit. You can even do this with a ruler and make the wave perfectly triangular. That's acceptable. I'm going to try to get my art hand on. There we go. Do not miss the dots. There we go. Good. Done. 2 out of 2. If you want to draw a second wave, notice you don't have to. But if you want to, you better measure it out. Because if your first wave is good and your second wave does this, you're like, oh, I know what to do now. Yeah, I got it. Yeah, there it is. Guess what? You missed and you didn't even realize it. Miss, no credit. So, if you're going to do a second wave, again, make this your new 0. 1, 2, 3, 4, 5, 6. There it is. Cross point is in between. Crest is in between those. Trough is in between those. And connect, and do not miss the dots. If you miss the dots, erase it and fix it. Okay, good. More commonly, as of late, have been these, the superposition graphs. They're pretty straightforward. Superposition just means lay them on top of each other and add, as you would expect. So this one, notice, has an amplitude of 1 meter, and this one is -0.4. So if you have 1 -0.4, add them together, of course, you get 0.6. So here's your 0.6, go up to 0.6, there it is, done. Often multiple choice also shows up this way. Again, this is similar to what you saw above. Just imagine, here's a hole. Here's the amount that can fill the hole, and then here's the leftover. That's really what a resultant wave or a superimposed wave or superposed, sometimes they call it, will look like, which of course gives you choice too. All right, we're getting there. We're getting there. Stick with us. How do I draw field lines? This is a pretty easy one. Now, the thing to watch out for, there are 3 different fields, and occasionally the exam likes to check that you know which one they're talking about. For all of them, the field line, it's a vector. They're all vector fields, and it's always an arrow with an arrowhead. And you must touch the surface of the object. Okay, now here, gravitational field, most of you probably just remember, but we basically have 3 test particles. Give them a little personality. Gravitational field depends on massy. Electric field depends on posi. Magnetic field depends on northy. What those are is just a mass test charge, a little tiny mass. Posi is a positive test charge, so imagine kind of like a proton, a little positive thing. And northy is a little north pole, almost like a compass, tiny little compass. So let's go check these out. Sometimes you actually have to draw them. So here's one. Sketch at least 4 magnetic field lines around the bar magnet. So what are they looking for? Well, if you're not sure, take northy and put it on. Let's put northy over here. Where would northy go if near a north pole? Well, like poles repel, similar to like charges repel. So northy would run away. They want 4 lines, so here's what we do. 1, 2, 3, 4. If you put northy by the south end, northy, of course, will attract. We'll put the 4 over there. 1, 2, 3, 4. Notice I'm trying to just touch the surface. Now, what do you have to do? Connect them. So it goes out from the north, and northy wraps around, comes into the south. Send these 2 above, then send these 2 below. Now, warning, I'm going to undo 2 of these. You may have done something like this. And then you got to do this one, and you start crossing over. Field lines never cross. You cannot have 2 different values at the same location in space. Field lines do not cross. So if you cross, erase them, think about it a minute, and try to find a way so that they don't cross. That way, of course, would be like this. Another thing to worry about, which occasionally is asked, is which way would a compass point here? And actually, a compass is northy. So if you put a little north pole there and see what it does, well, a north pole would repel from the north end. It would push it this way. A north pole would attract to the south, so it would pull this way. Well, what's the resultant of up left and down left? Well, the resultant there, of course, is just left, which, if you notice, matches the way the field line is going there anyway. Okay, so northy really does it for you. Here's another problem like this. Which one of these is correct? Well, you can actually think about it. If this were northy, northy would run away from a north, but toward a south. Here, if this were northy, it would run away from a north, but toward a south. Those 2 aren't it. Here, if this were northy, northy would run away from a north. So this must be a south. Here, this is coming in, northy coming in. Well, this must be a south too. Over here, northy would run away from a north. Northy would run away from a north. There's your answer choice. Another common one they ask is the electric field. And often they ask for the electric field between a positive negative plate. However, you could also have this. Of course, it's overheating. This is sweat game. You could have this with point charges as well, just like the questions up here. And so, actually, a nice challenge for you. Imagine these as charges. What would they be? Because the field lines, all these up here, the field lines for the electric field are very similar to the magnetic field. So hint, you put posi here. Posi runs away from positive. This would be a plus. Posi runs away from positive. This would be a plus. So you can run through that up top. Make sure you know what you're talking about. Anyway, here's an easy one. Put posi. What would posi do? Away from plus toward minus. Just touch the surfaces. There it is. Often they ask you to do 3 or 4 field lines. Please do exactly what they say. So you're asked, draw at least 3 field lines. Then draw 3. Okay, there it is. Here's another one, similar to what I was asking you to do up above. You can play the same game with if these were poles. All right, so posi would run away from a positive. You see the arrow going away? That's good. Posi would not run away from a negative. This has to be a positive. Here, posi would not run toward a positive. This would have to be negative. This one is okay. Posi would come toward a negative. Here, posi goes away from positive. Oh, and look at this. Posi goes toward negative. Here, posi does not go toward positive. This must be negative. And here, posi does not go away from negative. This must be positive. There's your right answer. Finally, the one on gravitational field, beware. They're trying to mess with you with this answer. This is the right answer for the magnetic field. This would be magnetic field, good to go. But the question didn't ask for the magnetic field. It asked for the gravitational field. And the way you do that is with massy. So put a little mass. Where will the mass go? Well, gravitational field is always attractive, so that's the easy one. Put a little mass over here. Of course, it would go in toward the Earth. If you put a mass here, it would not go away from the Earth. That doesn't happen. And masses do not have any interest in south going to north and north going to south. Here's your answer. Okay, almost done. The last section of pencil game. How do I draw a velocity vector here? Or any other force vector like acceleration, any other vector, excuse me, like acceleration, force. Well, of course, it has to be straight with an arrowhead. Be careful. Make sure it's the right length. Do not put a sloppy arrowhead on there. Sometimes you have to scale it. But even if you don't, even if it's just scratch work, try to make it roughly to scale. Now watch out with the circle problems. They like to ask about the different vectors. And they also like to ask about which way the wave, the medium, will go next. So let's look at a couple of those real quick. This one's been a staple lately, meaning it shows up all the time. The diagram shows a transverse wave. Transverse, of course, means, starts with a T. Let's make it a capital T. Flip it over, perpendicular. That means the medium vibrates perpendicular to wave motion. So if the wave is going to the right, so if motion is right, the vibration can only be up and down. Do not pick left, right, diagonal. It cannot be, no matter what your eyes tell you. If it's transverse, the vibration must be perpendicular to wave motion. All right, so where will it go next? Well, the easiest way to know this is just say whatever's approaching it. Here's point P. What's approaching it is this part. That's an uphill, which means the point will be pulled up next or to the top of the page. Just look at what's coming next. Another way is I traced over this wave. I'll move the wave over a little bit in the medium because that's what happens. The wave goes through the medium. It's not the medium riding the wave like a roller coaster or some nonsense. It's not what it is. This little point P does not come rolling down the hill. The wave goes through the medium this way, and it yanks on the medium. So as the wave moved just a bit to the right, as you see here, notice point P will get pulled up to this location. There's your top of the page. Down here's another one, very similar. Draw which way it'll go next. Well, this is certainly transverse, so perpendicular. If the motion's to the right, the vibration has to be up, down. And so where will this one go next? Well, look at what's approaching. An uphill is approaching. This one will go up. Let's look at a few of these. This one, that's an uphill too compared to where it is. That would go up. This one, well, that's a downhill. So this one's going to go down. This one, that's a downhill compared to what it is. That'll go down. Up, up, down. Think about that a bit. Whatever's approaching it is where it will go next. Another common situation for these velocity vectors is the circular problem. Now, they used to just ask questions like this one down here, which is, here's the car, give us the direction of whatever. If it's circular motion, by the way, circular motion, there's always an FC, and the FC is the net force. So they may say, which way does the centripetal force, or which way does the F net point? Well, those you know. It's FC. Let C tell you center. Which way is the FC point? Toward the center. There's FC. Which way does the AC, the centripetal acceleration point? Well, AC got a little c, toward the center. Answer, toward the center. This question actually asks for the direction of the velocity. The velocity is always tangent to the circle, which means it hits at just one point. So here, we know here's our car. Tangent has to be this way. And you may say, oh, wait, how did you know that? Well, let's check out based on our rule. Tangent also, well, let's look at this first. If you put a little bit of an angle like this, notice it hits the circle at two locations. That's not tangent. Another way is the tangent is always perpendicular to the radius at that point. So if the radius is right here, tangent must be perpendicular. Tangent is this way. Of course, you need an arrowhead on it. Well, the arrowhead just goes with the direction of the motion. So if the car is going around this way, which is counterclockwise, then of course up here, the motion is to the left. That would be your velocity vector. Now, recently, we've been playing a little game. It's kind of a nice question here, like question 61. What's the direction of the velocity at the instant that the acceleration is south? That's a bit of a mouthful here, but you got to pay attention to what it's saying. When the acceleration is south, then tell us the direction of the velocity. Well, let's check it out. It's very easy to know the direction of the acceleration. Like, for example, here the acceleration is always toward the center. That's north. Well, that's not south, so that's not the right location. Here the acceleration, always toward the center, is east. Well, that's not south, so that's not it. Here, the acceleration, always toward the center, is west. Well, that's not south, so that's not the location. Here, the acceleration is toward the center. That is south. This is the location we want, but the question is not over yet. Now, determine the direction of the velocity at that location. Well, the velocity, of course, is tangent here, and then perpendicular to that central or that radial. And then which way it goes with the rotation. So this one is clockwise, and the answer is east, or to the right. So watch out. That's been a popular one. Woo! That was an earful for you, a mouthful for me. So, yay! You're done with part 4. Congratulations. And we hope to see you during the next part of our video, part 5. Our video series, Physics, Regents, Physics, Warmup.